All right. Now that we've talked about inductance and what it is, we're going to look at the function of inductors and circuits. And we'll begin by looking at something known as an L over R circuit and determining what the short and long-term behavior is for these types of circuits. Just like we did the same thing with RC. So this will just be noticing it's a lot of the same problems as we do with capacitors. We just changed out the circuit component. So first up, we're just going to look at the short and long-term behavior of connecting a battery, resistor, and inductor in series. So first thing we're going to do is we're going to flip the switch, and we want to explain why, without using any sort of math and just kind of using understanding of inductors, why this should result in no current or nearly no current when the switch is first closed. Meaning the current is not going to start at a large value. And to look at this, remember that inductors oppose changes in current. So as soon as we flip the switch, the battery is going to attempt to send a huge current change through the inductor. And as a result, there will be a huge resistance in that back EMF of the inductor, effectively canceling out that effect initially. So we can see that here when the switch is first closed, the battery attempts to send a large current through the circuit. And as such, the inductor resists that change in its flux, resulting in no current initially. But then, at long times, the current will actually begin to slowly increase until reaching some steady state value. And this is the same thing going on, because if this inductor resists the change in current, well, that's going to make the change in current go down, which is going to cause the back EMF to go down, which is going to cause the rate of current change to keep going down at some sort of decaying rate until we eventually get a steady state value. So the inductor will oppose the battery EMF, causing the rate of increase of the current to decrease. So as a result, the inductor will gradually reduce its back EMF, which will eventually decay to no back EMF. So looking at this, our short and long time behavior of the inductor is in the short time, an inductor resists the change in current, which prevents current flow. But in the long time limit, the inductor doesn't really see that di dt anymore. And as such, it no longer produces a back EMF, meaning the current can freely pass through the inductor, and the inductor no longer minds. So now we're going to draw circuit diagrams without inductors that show the short and long time behavior. So basically, we're just saying we need something in the short time that is going to block the current, and we need something in the long time that is going to allow current. And remembering what we did with capacitors is going to make this quite easy to make this logical jump here. So something that blocks current, well, that's just going to be a gap. So I'm going to draw my resistance here. Again, my inductor would go in this spot right here that there's a gap. So I'm just going to redraw that twice. And then we'll fill in or not fill in those gaps with something that mimics the behavior that we're looking for. So first, if we're looking for something that blocks current, well, that's just going to be a gap. So I'm just going to put my X's here so I know it's not a mistake and that there actually should not be any sort of connection there. Because again, notice no current flows if there's a gap right there. But if we want to allow the current, well, that's just a wire. So it behaves like a short circuit. Also, we could look at this in the lens of resistance, where there's infinite and zero resistance, respectively. So first, we have the inductor blocking the increasing currents, and then we have no rate of current change. So even though there is current in the circuit, the inductor is perfectly fine with that because it's not changing. So this allows us to make our simplification as we did with capacitors. So our t equals 0 and t equals infinity models look like exactly what we produced on the other page, where an inductor that's storing energy exhibits opposite behavior of what a capacitor does. So an inductor works to block the current initially, but then it allows all current to flow as it successfully lowered the di dt value to 0. So this is opposite of capacitors, where short-time capacitors behave like wires and long-time capacitors behave like gaps. So this is our simplification that we'll use for short and long times. And as per usual, the in-between times are going to be some exponential relationship that we typically need a differential equation for, so we'll save that for next time. But these are our extreme cases. So an unhappy inductor will just behave like a gap, and then once it is sufficiently reduced the rate of current change, it will just behave like a short circuit. All right. So now we'll analyze this qualitatively and quantitatively. So we have a 200 millihenry inductor in series with a 50 ohm resistor and 10 volt battery, and there's a switch that can be closed. So first, we'll calculate the current through the inductor when the switch is first closed, and then when it's been closed for a long time. So again, using our rules for inductors here, we know that short times, it's going to behave like a gap to oppose current flow. So this will just be a gap. If I could, there we go. If I could actually write properly. So this would be a gap. So our redrawn circuit would essentially look like this. Let me check my resistance, 50 ohms. And then we have our gap in the wire where the inductor is, like so. So I think we can see from this diagram that it is pretty clear that the current through this circuit would be 0. Because there is a gap in the circuit, and as such, the current cannot flow. So this would be 0. And then a long time after the switch is closed. So we're just gonna, for time purposes, copy paste the diagram and make some minor adjustments. So in the long time, it no longer behaves like a gap, but instead, it will just behave like a standard wire. So then we can just apply Ohm's law to this circuit and get I is just going to be delta V divided by R EQ. And across our resistor, it's just the battery EMF divided by the resistance, which is going to be 10 volts divided by 50 ohms, which is just 0.2 amps. So notice that as we thought, we'd get 0 current at the start and then at some maximum value. Then find the magnitude of the potential difference across the inductor at each of these times. So once again, I think that we will just steal these diagrams. And now we will do some nice color coding here. So again, remember that there's no current flow at the start. So if there's no current flow, there can be no potential drop across my resistor. So I know that all of my potential drop must be across the inductor at the initial time here. Because again, to get a potential drop across the resistor, we need current. So we get no color change here, meaning delta V across the inductor is the full 10 volts of the battery to satisfy the loop rule. And then similarly, at the long time case, we do have current. And more importantly, we don't have any sort of changing current. So what that's going to do is mean that the inductor will not have any potential difference across it. So notice that there is no color change across my inductor in the second case, but there is in the first. So as with capacitors, we see that the voltage across the inductor and the resistor are constantly trading, and in different extreme cases, we either get zero potential difference or the full battery. And again, it has to work that way to satisfy the loop rule. And then calculate the energy stored when the switch is first closed versus a long time after the switch is closed. So our energy storage formula for an inductor is this kinetic energy lookalike term here, this 1/2 Li squared. But again, there is no current initially. So the reason inductors store energy is because there's current, which generates a magnetic field that stores energy. But then a long time after the switch is closed, it is the same expression. It's the magnetic field that's storing energy, 1/2 Li squared. But we do have a current, so we do actually have to work this out. So again, just looking at our values specifically, we have a 200 millihenry inductor, so 0.2. And then we also had 0.2 amps of current in steady state. So doing this, we get, let's see, can I do this without a calculator? We have 1/5 cubed, which would be 1 over 125, and then half of that, which would be 1 over 250 joules, or 0.004 joules of energy stored right there. All right, now we'll do a short and long time analysis of a couple numeric examples. So first we have a series circuit, and we're just going to basically calculate any quantity we could want at both times. So kind of drew some skeletons here, and then we have to insert the relevant connector. So for short times, inductors block current flow, so that would be like a gap in the wire. And then at long times, inductors allow the current to flow because there's no current change anymore. So that would be a short circuit. So now we'll start just by color coding the potential of the short time. So there's no current flow because of that gap, meaning we can't be dropping any sort of potential across either resistor. So as such, the entirety of the battery's potential must be dropped across the inductor. So doing our little short time analysis here, we see that there is no current. We see that delta V across both resistors, the 40 and the 60 ohm, are 0, because if there's no current through a resistor, there's no potential drop. This will also make the power 0. But the only real non-zero quantity here is delta V across the inductor, which is the full battery voltage of 20 volts. Now for the long time analysis, we see that this inductor is essentially a short circuit now. So when color coding our potential, we see that we just have a simple series circuit. So I do need a third potential color here. So first thing we should do, since it's a series circuit, is just calculate the total current. So the total current is just going to be the battery EMF divided by the equivalent resistance of the circuit, which would be those 20 volts divided by the two resistances added in series. So 20 divided by 100, which would be 0.2 amps. Then to calculate delta V across each resistor, we're just going to do Ohm's law. So multiplying delta V equals IR for each resistor. For the 40 ohm, it's just the 0.2 amps times 40, which would be 8 volts. And then delta V across the 60 ohm would be the same calculation, except with 60 ohms. And then since the inductor is a short circuit, there's zero EMF induced across it. And we'll calculate the other relevant quantities next. So first, notice the loop rule is satisfied because our 12 plus 8 volts does in fact equal the battery's voltage of 20. So filling in, at short times, we said there was 0 amps through either resistor, meaning there's 0 voltage drop, and that means that there's 0 joules per second of energy being dissipated. Across the inductor at that time, however, we had to drop all 20 volts, but it still blocked all the current flow, so it couldn't be storing any energy. At long times, however, we said that the 40 ohm dropped 9 volts, the 60 ohm dropped 12 volts. Both of them received the same series current of the battery of 0.2 amps. And then we can just multiply these out to get 1.8 watts of power and 2.4 watts of power, respectively. Because again, power, there's 3 ways of writing it, but given the information we have here, I delta V, the definition is probably the easiest. All right, then for the inductor, at long times, there is no voltage drop because it's a short circuit, and it was at the same potential as everything around it. The current through, however, was non-zero, it was 0.2 amps. And then applying the inductor energy formula, 1/2 Li squared, we get 1/2 times the inductance of 0.8 times the current of 0.2. So working that out, that gets us let's see here, 0.016 joules. So that's everything with that circuit. Next, we'll deal with a parallel case, which looks very similar, except it's resistors in parallel. So once again, the short time case of the inductor, it will block the current flow, so it's a gap. And the long time case, it will allow current flow because there's no current change. So that's just a short circuit. All right. Now for color coding, the short time, we see that there's no current still because you can't form a complete loop. So as such, we get 0 potential difference across each resistor, which means that all the potential drop has to be across the inductor. So we see that delta V across the 200 ohm is the same as the delta V across the 40 ohm, which is 0 volts. We also see that the total current is 0 amps. And based on our diagram, the only sort of real non-zero value is the delta V across the inductor, which is the full battery voltage. Then if we go over here, we do get a change, of course, because now, due to the short circuit, we do have closed loops, and we actually have 2 closed loops. So This allows us to just use Ohm's law to calculate each current. I'm actually not going to find REQ here because we can find the total current using other methods. So just to find the current through each branch, we'll start with the 40. So the 40 ohm resistor, again, just do Ohm's law, delta V over R. And we get 40 as our resistance. So 10 divided by 40, which is 0.25 amps. And then for the current through the 200 ohm resistor, it's delta V over R, but we have 5 times the resistance now. So it's 1/5 the current. And then notice if we wanted the total current, we could just add these two together because of Kirchhoff's junction rule. We know that the battery is supplying 0.3 amps of current. And this is what you get if you find REQ. Okay, and then we see that at long times, this would also be the current through the inductor, which has 0 voltage drop. All right, so we'll just circle these values and then we'll fill in the table. So again, just due to the fact that we had a parallel circuit, it made more sense just to calculate the currents individually and then add them with the junction rule. So going through, due to the nature of the parallel circuit, both resistors had to drop the full battery voltage of 10 volts. The current through each resistor was changed, though. The smaller resistor required more current. And then just multiplying to get the power dissipated by doing I delta V, we get 2.5 watts. Oh, and I put this in the wrong spot. We'll copy this. We'll do this one first. 2.5 watts, and then 0.5 watts. Notice that works out because we have 10 volts from the battery and 0.3 amps, so that does give the total power to work out. We said there's 0 voltage drop across the inductor at this time, but it receives all of the current. And then just computing the energy stored via 1/2 Li squared. We just get 0.5 times 0.005 times 0.3 squared, which is 2.25 times 10 to the minus 4. Joules. All right, now for the short times. Well, we had no current through the circuit, so we didn't drop any voltage across either resistor. And as such, we also were not dissipating any power or dissipating energy. The inductor, however, opposed the current change, so it had an EMF of 10 volts across it, but it did not store energy. All right, last numeric example. We have a series parallel kind of combination here, so we will get interesting results for both times. As per usual, inductor at short times behaves like a gap. Inductor at long times behaves like a short. So, short time analysis. We once again see that the inductor serves as a gap. So doing my little color coding here, we see that no current can go through that gap. So we essentially just create a series circuit. So to find the current, we just divide the battery voltage by the equivalent resistance. And this is not 10 volts. It's 12 volts. So we get 12 over 40 for our current, because we have 12 volts divided by 10 plus 30 ohms in series. And that would be equal to 3 divided by 10, so 0.3 amps. And then we'll just do Ohm's law for each. So delta V across the 10 ohm is just I times R. So multiply that current by the 10 ohms of resistance, and we get 3 volts. But then if you multiply the 30 ohm resistor by its current, we get 9 volts. But then, this is where it gets more interesting, the potential difference across the inductor. It usually was the full battery voltage in this situation. But notice, either due to the color change or due to the parallel rule, the inductor, its potential colors also go from yellow to blue, just like it does across the 30 ohm because of the parallel nature of it. So it actually shares the 9 volts of potential difference across it because it's in parallel with the 30 ohm. And my mouse is like lagging. That's interesting. Okay. And now for the long time analysis. So for the long time analysis, notice we have this sort of short caused by the inductor. So actually, due to the fact that it's a short circuit, notice we actually get the color blue on both sides of the 30 ohm resistor. So as such, it is effectively shorted, and it's just removed from the circuit entirely. So we just have all 12 volts being dropped across the 10 ohm resistor. So again, this loop is essentially just cut off then. So I would just be the 12 volts divided by the 10 ohms, which is 1.2 amps. So it drops all 12 volts, and then as a result, delta V across the 30 ohm is 0 volts, and also there's no color change across the inductor at this point, so delta V across the inductor is also 0 volts. All right, so now we'll just circle these values. All right, so short times. The current through both resistors was 0.3 amps. IR for the first one gave us 3 volts. IR for the second resistor gave us 9 volts. Notice they add up to 12. Power dissipated just by doing I delta V is just 0.9 watts. And 2.7 watts, respectively. And notice this adds up to 3.6, which is exactly what you get when you multiply the battery voltage by the battery current. At this time, the voltage drop across the inductor was 9 volts because it was in parallel with the 30 ohm. The current through it was 0 because it still blocks current, and the energy stored was 0 because there was no current through the inductor. At long times, we said that the 30 ohm was effectively shorted. So that means that we get all zeros from 30 at this point. The voltage drop was the full battery voltage across the 10 ohm resistor. So the current through it was just 12 volts divided by 10 ohms, so 1.2 amps. And the power dissipated is just those two numbers multiplied together, which is 14.4 watts. And then for the inductor, there was no voltage drop across the inductor because it was a short circuit. The current through the inductor was the the current through the inductor, if we go back and check here, is the full battery current, 1.2 amps. So the energy stored by this 20 millihenry inductor is therefore just going to be 1/2 Li squared, so 0.5 times 0.02 times 1.2 squared. And that is 0.0144. Get my units right. All right, then to conclude, we have the circuit shown below. It's definitely a complex circuit. There's a bunch of R's in series / parallel, but we're just asked to find the energy stored in the inductor's magnetic field at long times. And this is actually going to do a lot of good things for us. So at long times, this inductor is going to become a short circuit. So it's actually more annoying to find the initial current in the circuit because if the inductor's a gap, we have to include everything going on this right side. But at long times, the inductor behaves like a short circuit. And as such, if we were to color code our potential, we see that the entire right half of the circuit is actually just removed. Because we get this yellow color on both sides of all of these resistors. So effectively, this side of the circuit is just gone. So we're just given a very simple circuit to analyze, and we'll use the fact that the energy stored in an inductor is 1/2 Li squared. But the current through the inductor is just going to be the current through the circuit. And we know that current through the circuit is just going to be the EMF of the battery divided by Req. And Req for this circuit is just, well, 2 R's in series, so 2R. And then squaring everything, we get a 4 on the denominator, so combine that with the 1/2, and we get 1/8 times L times the EMF squared divided by R. Squared. And that's everything sort of steady state. Then we'll look at the differential equation part next time of actually getting the transient behavior of the increase and decrease of the current.